Part 1. The rule we thought would never break. Picture the most fundamental rule in the universe. Not gravity, not the speed of light, not even the conservation of energy. The most fundamental rule is this. The past is finished. It happened. It is done. It is locked away in the vault of history, sealed with a key that no force in nature can ever turn. The dinosaurs went extinct. Julius Caesar crossed the Rubicon. The first star ignited in the darkness of the early universe. These events are complete. They are over. They are beyond the reach of anyone, anything. We build our entire understanding of reality on this one bedrock assumption. Science depends on it. Logic depends on it. Our sanity depends on it. Every experiment ever conducted assumes that what happened in the past stays in the past. Every prediction ever made assumes that we are moving forward through a chain of causes and effects, each one neatly following the one before it, like dominoes falling in a single, irreversible direction. Cause comes before effect. Always. And then a physicist named John Wheeler sat down with a pencil and a sheet of paper, and with a few quiet lines of thought, he proposed an experiment that breaks everything, not metaphorically, not philosophically, physically, measurably, experimentally, in a real laboratory with real equipment and real data. The universe has been caught doing something that it, by every rule we hold sacred, should be completely unable. It has been caught making decisions about the past, based on what is happening right now. This is the story of delayed choice quantum eraser. It is not science fiction. It is not fringe theory. It has been performed. The data exists. The results have been replicated in laboratories across the world, in increasingly sophisticated and airtight versions, each one confirming the same deeply unsettling conclusion. The past, it turns out, is not always finished, and the universe is stranger than you have ever been told. Part 2. The strange education of a photon. To understand why the delayed choice experiment breaks the universe, you first need to understand what light actually is. And when I say actually, I mean not in the comfortable, simplified version you learned in school, but in the genuine, laboratory-tested, physicist-verified version that has been forcing scientists to rethink the nature of reality for over a century. Let us start at the beginning. In the early 1600s, a Dutch scientist named Christian Huygens argued that light was a wave. Picture dropping a stone into a perfectly still pond. The disturbance ripples outward in expanding circles, and when those ripples encounter other ripples from a second stone, they interact in a predictable way. Where the crests of two waves meet, they combine and make a bigger wave. Where a crest meets a trough, they cancel each other out and create a flat spot. This is called interference, and it is the signature behavior of all waves, from water to sound to light. Isaac Newton disagreed. Newton believed light was made of tiny particles he called corpuscles. These particles would travel in straight lines, bounce off mirrors, and refract through glass in ways that Newton could mathematically predict. His authority was so enormous in the scientific world that for 100 years, the wave theory was largely set aside. Then in 1801, a British polymath named Thomas Young performed an experiment that settled the argument. He took a light source, placed a barrier with two tiny slits in front of it, and let the light fall on a screen behind the barrier. If Newton was right, and light was a stream of particles, you would expect to see two bright bands on the screen directly behind the slits. The particles would pass through one opening or the other and land in a corresponding pile. Instead, Young saw something that Newton could not explain, something hauntingly beautiful. He saw stripes, alternating bands of brightness and darkness, spread across the screen in a pattern that could only result from waves interfering with each other. The light was passing through both slits simultaneously, emerging as two sets of waves that spread outward and crashed into each other. Where the peaks aligned, the screen lit up. Where a peak met a trough, the light canceled out and left a dark band. The light was a wave. For another 100 years, this seemed settled. Then Albert Einstein, in his miracle year of 1905, analyzed something called the photoelectric effect, in which light knocks electrons off the surface of a metal. The only way to explain the precise behavior of those electrons, Einstein showed, was if light arrived not in continuous waves, but in discrete packets of energy. He called them quanta. Later generations would call them photons. Light was a particle again, But Young's experiment was still producing those stripes. How could light be particles and still create an interference pattern? The answer that emerged from the development of quantum mechanics over the following decades was so strange that even the physicists who formulated it spent decades arguing about what it meant, and in many ways, that argument has never fully been resolved. The answer is this: light is neither a wave nor a particle. It is something that has no classical name, no everyday analogy, no comfortable framework in human experience. When we force it to itself through a measurement, it shows us one face or the other, depending on what kind of question we ask. But between measurements, in the darkness between one observation and the next, it exists as something genuinely different from either thing we have words for. Physicists invented mathematical machinery to describe this in-between state. They called it the quantum wave function, and it is not a wave in the ordinary sense of something physically rippling through space. It is a wave of probability. It is the mathematical description of all the possible states the particle could be in, weighted by how likely each state is to be found upon measurement. The photon does not take one path or the other. It does not secretly choose one slit and sneak through. It exists in a superposition of both possibilities simultaneously, its wave functions spreading out and interfering with itself as if it were a wave, right up until the moment it is observed. And then, in the instant of observation, the wave function collapses. The quantum fog of possibilities condenses into a single, definite reality. The particle materializes at one specific location. The stripes on the screen emerge from the collective behavior of millions of such individual collapses, each photon contributing its tiny mark to a pattern that, taken all together, traces out the unmistakable signature of wave interference. This is the heart of the mystery. The photon, as an individual, seems to pass through both slits at once. As a wave of probability, it interferes with itself. As a particle, it lands in one definite spot. The pattern it contributes to is a wave. The mark it leaves is a particle. How? The answer, as best as we can determine, is that the question assumes a kind of underlying reality that quantum mechanics suggests may not actually exist. The photon does not have a definite path between measurements. It is not secretly traveling one route while appearing to travel both. The path simply does not exist in a physically meaningful sense until something measures it. Which is where everything gets interesting. Part 3. The observer ruins everything, then makes it stranger. Let us go back to the dull slit experiment. The light is creating beautiful interference fringes on the screen. We know the photons are passing through both slits as waves of probability, and those waves are interfering with each other. Now suppose we get curious. We want to know which slit each photon actually goes through. We have the right to ask this question. We set up a detector right at the barrier, a clever little device that can register the path of a photon without disturbing it too much, just enough to tell us which slit it used. We run the experiment. The detector beeps. It tells us that photon after photon is going through one slit or the other. We look at the screen behind the barrier. The stripes are gone. Where before we had a gorgeous interference pattern, now we have two simple bands of light directly behind the two slits, exactly as Newton would predicted particles. The moment we place a detector to observe the path, the wave behavior vanishes. The photons stop spreading through both slits and start going through one or the other. The interference, which requires the photon to take both paths, disappears as soon as we create the conditions under which only one path is taken. This is the observer effect, and it is one of the most famous and most misunderstood phenomena in all of science. People often interpret this as meaning that the act of human consciousness somehow affects the behavior of particles. That we, as observers, as thinking beings, are causing the collapse of the wave function through the sheer power of awareness. This interpretation is poetic and has inspired enormous amounts of philosophical and spiritual speculation, but it is not quite what the physics says. What actually destroys the interference pattern is not observation in the sense of someone looking. It is physical entanglement in the sense of information. When we place a detector at the slits, the photon becomes entangled with the detector. The detector and the photon share a quantum state, which means the detector carries information about which path the photon took. This information, even if no human ever reads the detector's output, is sufficient to destroy the interference. The which path information exists in the physical world, recorded in the state of the detector, and the existence of that information, that correlation between the photon's path, and some physical record somewhere in the universe, is what eliminates the wave behavior. This is an important distinction, because it sets up the crux of the delayed choice experiment. If it is the existence of which path information that destroys the interference, then by implication, the absence of that information should allow interference to be restored. And here is the question that John Wheeler asked, in his quiet revolutionary way. What if we create the which path information and then erase it? And what if we do the erasing after the photon has already landed on the screen? Part 4. John Wheeler and the Cosmic Double Slit. John Archibald Wheeler was one of the most remarkable physicists of the 20th century. A colleague of Einstein, a teacher of Richard Feynman, the man who coined the term hole and helped develop the geometry of curved spacetime, Wheeler spent the later decades of his long career obsessed with a single question that cuts to the bone of what reality actually is. He called it the question of the it from bit. He wanted to know whether the physical universe, all the matter and energy and space and time of it, whether all of that physical stuff might ultimately arise from information, whether reality is, at its deepest level, not made of things, but of answers to questions. This was not idle philosophizing. Wheeler was trying to make sense of what quantum mechanics was telling him about the nature of measurement, observation, and the relationship between the observer and the observed. And in 1978, he came up with a thought experiment that has the power to stop a physicist cold, even today. He did not use a laboratory. He used the universe. Imagine a quasar. These are the brightest objects in the known cosmos, ancient engines of radiation that blaze with the light of a trillion suns, powered by supermassive black holes swallowing matter at the hearts of distant galaxies. Some quasars are so far away that their light has been traveling toward us for more than 10 billion years, since before our solar system existed, since before the Earth was formed. Between us and a distant quasar, imagine a massive galaxy. Not small massive, but genuinely, cosmically massive, the kind of object whose gravitational field is so powerful that it bends space itself. When light from the quasar encounters this galaxy, the fabric of space-time curves around the galaxy's mass, and the light bends with it. This is gravitational lensing, and it has a remarkable consequence. The light from the quasar can curve around the left side of the intervening galaxy, and it can curve around the right side. Both paths are available. Both paths lead to Earth. And so we receive the quasar's light from two slightly different directions, creating the appearance of two quasars where there is only one. Now here is what Wheeler understood. This is a double-slit experiment. The quasar is the light source. The galaxy is the barrier with two slits. The two paths around the galaxy, left and right, are the two slits. And we, sitting in our observatories on Earth, are the back wall where the pattern is recorded. The photons that are just now arriving at our telescopes left that quasar billions of years ago. They passed the intervening galaxy billions of years ago. They have been traveling through the void of intergalactic space for longer than the Earth has existed. And now, at this very moment, they are about to hit our detectors. And Wheeler asked, what if, at this very last moment, we choose how to measure them? We have two options. Option 1. We point our telescopes at the two separate images of the quasar. We measure which image a given photon came from. If it came from the left image, it traveled around the left side of the galaxy. If it came from the right image, it traveled around the right side. We know its path. We have which path information. Under this measurement, the photon must have taken a definite single path around the galaxy. It either went left or it went right. It was a particle. Option 2. We feed both telescopes into an interferometer that combines the light from both paths and looks for the signature of wave interference. If the light shows an interference pattern, the photon must have traveled both paths simultaneously. It was a wave, and the two wave paths of the single photon interfered with each other. Now here is the part that stops the clock. That photon passed the galaxy billions of years ago. At that moment, billions of years in the past, in some real physical sense, the photon either took a single path particle or both paths wave. That must have been settled before the Earth existed. The history of that photon, we assume, written at the moment it passed the galaxy. But Wheeler was saying that the history of the photon was not written until tonight. It is not written until the astronomer in the observatory makes the choice about which measurement to perform. The measurement made tonight, in the present, on a photon that has been traveling for billions of years, appears to determine how the photon behaved billions of years ago. The photon does not have a past until someone in the present decides what question to ask about it. Wheeler called this the delayed choice experiment, and it was, for 20 years, purely theoretical. It was too philosophical, too vast, too dependent on the bizarre timescales of cosmology to be directly tested. And then, in a laboratory in Baltimore, a team of scientists found a way to do it in a shoebox. Part 5, the machine that erases the past, the year, was 1999. The researchers were Yoonho Kim, R.U.S.B. Kulik, I.U.H. Shi, and Marlon Scully. The paper they published described something they called the delayed choice quantum eraser, and it took Wheeler's cosmic thought experiment and squeezed it down into a tabletop apparatus no larger than a modest desk. At the heart of the apparatus was a crystal. Not any crystal, but a beta barium borate crystal, a fascinating material with a specific and exploitable quantum property. When you fire a laser into this crystal, very occasionally, with a small but precise probability, something remarkable happens at the quantum level. A single photon from the laser is absorbed by an atom in the crystal, and the atom remits not one photon, but two. The original photon, with its particular frequency and energy, is split in two lower energy photons. This process is called spontaneous parametric down conversion, and its most important feature is that the two daughter photons are entangled. They are not just similar, they are not just correlated in a statistical sense. They are quantum mechanically linked in a way that has no classical equivalent. They share a single quantum state. What is true of one is, in a specific and mathematically precise sense, instantaneously true of the other, regardless of the distance between them. The researchers called one photon the signal photon and the other the idler photon. The signal photon had a simple job. Born from the crystal, it traveled a very short distance to a detector called D0. This detector was the equivalent of the back wall in the double-slit experiment. It recorded where the photon landed. That was its entire function. The signal photon hit the detector, left a mark, and that was the end of its story. The idler photon had a much more complex journey. It was sent in the opposite direction, into a carefully designed maze of optical components, mirrors, prisms, and most importantly, beam splitters. The path the idler photon traveled was physically much longer than the path of the signal photon. This length difference was deliberate and crucial. It created a time delay. By the time the idler photon reached any of its possible detectors, the signal photon had already been detected, recorded, and in a meaningful sense, was already history. The maze to four possible detectors, labeled D1, D2, D3, and D4. The geometry was designed to present a choice, automatically, through physics. If the idler photon traveled a certain route through the maze, it would end up at detector D or D4. These detectors were positioned such that their geometry preserved the which path information. If D3 clicked, the path was known. If D4 clicked, the path was known. The universe, in these cases, retained the information about which route the photon had taken through the earlier part of the apparatus. But if the idler photon traveled a different route, it would enter a beam splitter before reaching D1 or D2. A beam splitter is a half-silvered mirror that does something extraordinary to the quantum state of a photon. It scrambles the path information. A photon arriving from one direction leaves the beam splitter with a probability of going either forward or sideways, and the two possible paths after the beam splitter are quantum mechanically in a way that makes it impossible, even in principle, to determine which path the photon came from. The which path information is not just hidden, it is destroyed, erased, removed from the universe. And here is the question the experiment was designed to answer. The signal photon hits its detector first. The record of its landing position exists. The data is in the computer. Now, nanoseconds later, the idler photon is still traveling through the maze. Depending on which route it takes, the which path information will either be preserved at D3 or D4, or erased at D1 or D2. Does it matter to the signal photon that has already been detected what happens to the I photon in the future? Common sense says no. The signal photon is done. Its position has been recorded. Its story is over. Nothing that happens afterward to its entangled twin can possibly change where it landed. Common sense is wrong. Part 6. The data that broke the clock the experiment ran. The crystal fired. Photon pairs flew apart in opposite directions. The signal photons hit the detector D0 and left their marks. The Adler photons traveled through the maze. Some went to D3 or D4, preserving the path information. Others went to D1 or D2, erasing it. The data accumulated. Thousands of events, then tens of thousands, then hundreds of thousands. Each signal photon recorded with its position. Each Adler photon recorded with which detector caught it. The computer logged everything. Then came the analysis, and this is where the careful thinking becomes absolutely essential, because the results do not speak for themselves in the way you might expect. To see what is really happening, you have to look at the data in a very specific way. If you take all the signal photons together, every single one regard happened to what happened to their Adler twins, and plot them all on a graph, you see nothing unusual. Just a blurry, diffused distribution of impact points. No interference fringes, no wave pattern, nothing to see. The total, undifferentiated data set looks perfectly ordinary. This is not an accident. This is a deep feature of quantum mechanics that we will return to. But now you sort the data. You take all the signal photon detection events and you ask, for each one, what did the Adler twin do? You divide the signal photons into groups based on what happened to their partners. Group 1, Adler photon ended at D3. You filter out all the signal photons whose Adler twins went to detector 3. The which information for these pairs was preserved. D3 told you which path the Adler took, and by extension which path the signal had taken. You plot the landing positions of just these signal photons. What do you see? No interference. A simple clump of photons, distributed as you would expect for particles that definite paths. No stripes. No bands. Just a pile. Group 2, Adler photon ended at D4. Same result. No interference. Another simple clump of particle-like behavior. The which path information was preserved, and accordingly, the signal photons behaved like particles. Group 3, Adler photon ended at D1. Now you filter for the signal photons, whose Adler twins were sent through the beam splitter and caught at D1. The which path information was erased. There is no record anywhere in the universe of which path the Adler took. You plot the landing positions of just these signal photons. The pattern that appears on the graph is unmistakable. Alternating bands of high density and low density, the classic, undeniable signature of wave interference. The signal photons, whose Adler twins had their path information erased, show a perfect interference pattern. Group 4, Adler photon ended at D2. Same result with a slight positional shift due to the geometry of the apparatus. Another interference pattern, more stripes, more wave behavior. The conclusion is inescapable. The signal photon, which hit its detector first, behaved as a wave if its twin's information would later be erased. It behaved as a particle if its twin's information would later be preserved. The word would in the previous sentence is the problem. It implies that the signal photon, in the past, knew what was going to happen to its twin in the future. But that is exactly what the data shows, and it has been replicated in different laboratories, with different designs, with longer delay times, with more sophisticated equipment. Each experiment confirms the same thing. The future fate of the Adler photon determines the past behavior of the signal photon. The arrow of time, in this experiment, appears to be pointing in both directions at once. Part 7. Does actually mean. Let's be very careful here, because this is the point where popular accounts of this experiment tend to go off the rails. The delayed choice quantum eraser is genuinely extraordinary, genuinely disturbing, genuinely difficult to fit into any comfortable conceptual framework. But it is also frequently described in ways that are more dramatic than they need to be, and sometimes in ways that are outright wrong. Let us separate what the experiment actually shows from what it does not show. What it does show: when you sort the signal photons by the fate of their Adler twins, you find a perfect correlation. The signal photons Adler twins had their path information erased show interference. The signal photons whose Idler twins had their path information preserved show interference. This correlation exists regardless of the time ordering. The Idler is detected after the signal, yet the Idler's fate correlates with the signal's behavior. This is a real, measured, reproducible effect. What it does not show that information traveled backward in time. It does not show that you can use this effect to send a message to the past. It does not show that consciousness controls reality. It does not show that the past can be physically changed. Here is why. When you look at the total, unsorted data, at all the signal photons together, there is no interference pattern. There is no pattern at all. Just a featureless blob. If you are standing at the detector D0 watching in real time, you have no way of knowing where a given signal photon is going to end up in the interference subgroup or the no interference subgroup. You cannot tell, from the behavior of the signal photon alone, whether the which path information for its twin is going preserved or erased. The patterns are hidden. They are encrypted inside the noise of the total data set. The only way to reveal them is to sort the signal photons using the Idler data, and the Idler data does not exist until the Idler photons have been detected. In other words, you cannot see the effects of the future measurement until the future has actually happened and its results have been brought into the present. You cannot use this to send information to the past because you cannot see anything meaningful in the past data until you have the future data to sort it with, and by then both events are in the past. The timeline is protected, not by some superficial rule, but by the deep structure of quantum mechanics itself. The technical name for this protection is the no communication theorem. It is a mathematical proof, not just a rule, that the correlations produced by quantum entanglement, no matter how strange they seem, cannot be used to transmit information faster than light or backward through time. But the no communication theorem does not make the experiment less mysterious. It just changes the nature of the mystery. The mystery is not that the past can be changed. The mystery is that the past did not appear to be definite in the first place. Part 8. The nature of quantum entanglement. To truly grasp what the delayed choice quantum eraser is showing us, we need to understand entanglement at a deeper level than spooky action at a distance, which is how Einstein dismissively and unforgettably described it. When two particles are entangled, they do not have separate, independent quantum states. They share a single joint quantum state. This shared state is a superposition of all possible correlations between the two particles, and it exists as a whole, as a single mathematical object, even when the particles are separated by large distances. This is not just poetic language. It has precise mathematical content. The state of an entangled pair cannot be written as the product of the states of the individual particles. The particles are not individually in states. They are collectively in a state, and that collective state is a fundamental, irreducible feature of the system. What this means, for the delayed choice experiment, is that when the signal photon hits its detector, the measurement event does not happen to the signal photon alone. It happens to the entangled system. The joint quantum state of the signal-Idler pair begins to evolve in a way that is correlated with the signal photon's measurement outcome. But it does not fully collapse in the relevant sense until the Idler photon is also so measured. This is deeply counterintuitive. We are used to thinking of events as happening at definite times and places. When the signal photon hits the detector at time t, we think that is when and where its story ends. But if the signal and Idler are entangled, the story of the system, of the entangled pair, does not end until both photons have been measured. The correlations we observe between the signal's landing position and the Idler's detector are not the result of information traveling between the photons at the moment of measurement. They are the result of correlations that were built into the joint quantum state from the very beginning, at the moment of creation, when the original photon was split in the crystal. And this is crucial, the specific correlation that manifests depends on what measurement is performed. The joint state contains all possible correlations in superposition. When the Idler is measured in a way that preserves the path information, the correlations that unfold are consistent with particle behavior in the signal. When the Idler is measured in a way that erases the path information, the correlations that unfold are consistent with wave behavior in the signal. The history does not change. Changes is which history, always implicit in the quantum state, becomes manifest. It is as if the photon pair were a sealed envelope containing both possible stories all along, and the measurement of the idler is the act of opening the envelope and choosing which story to read. Part 9. Reality as a negotiation. There is a school of thought in the interpretation of quantum mechanics, associated most famously with the Danish physicist Niels Bohr, called the Copenhagen interpretation. In its most radical form, it says something extremely uncomfortable. It says that there is no fact about unmeasured quantities. The photon does not have a definite path between measurements. It does not secretly travel one route while appearing to travel both. It is not the case that we simply do not know which path it took. It is that there is nothing to know. The path does not exist as a fact about the world until a measurement is made to establish it. This is the view that Einstein hated. Einstein spent decades arguing against it, designing thought experiments intended to show that quantum mechanics was incomplete, that there must be hidden variables, underlying definite values that quantum mechanics simply did not have access to. He believed in what he called local realism, the idea that physical objects have definite properties whether or not anyone is measuring them, and that influences cannot propagate faster than the speed of light. He was wrong. In the 1960s, the physicist John Bell devised a mathematical theorem that made the dispute testable. Bell showed that if Einstein's local realism were correct, then the correlations between measurements on entangled particles would have to satisfy certain mathematical inequalities. He derived the bounds on how correlated the measurements could be if there were underlying definite values. Subsequent experiments, most famously by Alain Aspect in the 1980s, and confirmed by increasingly rigorous experiments up to the present day, have shown that nature violates Bell's inequalities. The correlations are stronger than any locally realistic theory can account for. Einstein's hidden variables do not exist, at least not in any form compatible with the measured facts. The universe, at the quantum level, is not locally realistic. The delayed choice quantum eraser is perhaps the most viscerally dramatic demonstration of what this means in practice. Not just that particles are correlated in ways that exceed classical expectations, but that the act of measurement in the present appears to reach into the past, give it a specific character that it did not have before. The particle did not travel this path or that path before it was measured. It traveled a superposition of paths. The past, in the relevant sense, was indeterminate, and then we measured it, and the past became definite. Bohr, if he were alive today, might say something like this: the delayed choice experiment is not showing us that the past changes. It is showing us that the past did not have a definite form until the future acted on it. The question, which path did the photon take billions of years ago, does not have an answer until someone today creates the conditions under which an answer can be given. Wheeler expressed this view in his famous participatory universe hypothesis. He argued that the universe does not exist out there independent of all observation. Instead, the universe acquires its specific character through the act of observation. We are not merely witnesses to a cosmic drama that was written before we arrived. We are participants. Our questions create the answers. Our measurements bring the facts into being. This is not idealism in the philosophical sense. It is not claiming that the universe only exists inside our minds. It is claiming something more subtle and more unsettling, that the universe's definite properties only crystallize when they interact with something else. The photon is not a solid thing with a definite location and trajectory moving through space. It is a quantum system, a set of potentialities, and it becomes definite only in the context of an interaction. And that interaction, as the delayed choice experiment shows, can determine what the quantum system was doing before the interaction occurred. Part 10. The many worlds alternative, the Copenhagen interpretation, is not the only way to make sense of quantum mechanics, and many physicists find it deeply unsatisfying. The idea that quantum systems do not have definite properties until measured is, to many people, simply too strange to accept. It seems to privilege observation in a way that puts the cart before the horse. It seems to imply that the universe was somehow indeterminate for the first 9 billion years of its existence, waiting for complex enough observers to emerge before anything could be definitively said to have happened. One of the most popular alternative interpretations is the many worlds interpretation, proposed by Hugh Everett in 1957. In the many worlds view, the wave function never collapses. Measurement does not force a quantum system into a definite state. Instead, every time a measurement is made, the universe branches. Both outcomes happen in different branches of a vastly expanding tree of parallel realities. In one branch, the photon went left. In another branch, the photon went right. You, the observer, also branch. One version of you sees the photon go left. Another version sees it go right. In the many worlds picture, there is never any indeterminacy in the sense of genuinely undefined values. All values exist in all branches. The interference pattern in the double-slit experiment arises because the branches of reality interfere with each other, just as waves interfere. How does the many worlds interpretation handle the delayed choice experiment? At the moment the signal photon is detected, the universe branches into all the possible outcomes, all the possible positions where the signal photon could have landed. Each branch is real. Each version of the experiment continues in its own branch. Later, when the idler photon is measured, the universe branches again, based on which detector catches the idler. In the branches where the idler goes to D1 or D2, the which path information is erased. In the branches where the idler goes D3 or D4, the path information is preserved. Now comes the sorting. The researcher in each branch looks at the signal photon data and sorts it by the idler outcome. Because the branches where the idler's information is erased are also the branches where the signal photon's quantum state was such as to produce an interference pattern. When you sort the data, you find the interference pattern in the erased subgroup and the no interference pattern in the preserved subgroup. The many worlds picture does not require any backward causation. The correlations are built in from the start. The branching structure of the wave function naturally produces the correlations we observe when we sort the data. No information travels backward. No past is changed. The delayed choice experiment, in the many worlds view, is strange but not paradoxical. Whether this makes you feel better or worse probably depends on how comfortable you are with the idea of trillions of parallel universes branching off every second. Part 11. The pilot wave and other roads not taken. There is another interpretation that deserves mention. Because it takes a radically different approach to the problem of wave-particle duality, and it illuminates the delayed choice experiment from yet another angle. It is called the de Broglie theory, or the pilot wave interpretation, after the French physicist Louis de Broglie, who first suggested it in 1927, and the American physicist David Bohm, who fully developed it in 1952. In the pilot picture, particles are always particles. They always have definite positions. They travel along definite paths. There is no wave-particle duality in the sense of a single entity being sometimes a wave and sometimes a particle. Instead, there is a particle which always travels a single definite path. And there is a pilot wave, a real physical wave in configuration space that guides the particle's motion. The pilot wave is real. It propagates through both slits simultaneously. It sets up the interference pattern in the space behind the barrier. But the particle, guided by this wave, travels through only one slit and lands in one definite location. The interference pattern in the double-slit experiment is not caused by the particle interfering with itself. It is caused by the pilot wave shaping the statistical distribution of where the particle can land. When we place a detector at the slits, the detector interacts with the pilot wave and alters its form. The interaction destroys the interference structure of the wave. The particle, now guided by a wave with no interference pattern, lands in a distribution with no stripes. In the pilot wave picture, the delayed choice experiment is handled differently than in Copenhagen. The particle always had a definite path. What the measurement of the idler photon determines is not the path of the signal photon, which was definite all along, but which signal photon sorted to its subgroup. The interference pattern was always there in the total data, hidden in the structure of the pilot wave. The measurement of the idler after the fact determines which photons belong to the subgroup that, taken together, traces out the interference pattern. This sounds, on first hearing, like it might be explaining away the strangeness. But the pilot wave picture has its own profound strangeness. The pilot wave is non-local. It responds instantaneously to measurements made on distant parts of the system. The wave in configuration space is not a wave in ordinary three-dimensional space at all. It exists in the full multi-dimensional configuration space of all the particles in the universe simultaneously. The non-locality is the price you pay for keeping particles as definite things with definite trajectories. Every interpretation of quantum mechanics, whether Copenhagen, many worlds, pilot wave, relational, or any of the others, preserves the same mathematical structure and the same experimental predictions. The universe refuses to show us the underlying machinery. The data is consistent with all of them, and inconsistent with none of them. What the delayed choice experiment does, across all these interpretations, is force us to confront the non-classical nature of that mathematical structure head-on. Whether you say the past was indeterminate until the measurement Copenhagen, or that all stories coexist in parallel branches, many worlds, or that the non-local pilot organizes correlations across time, pilot wave, the result is the same. Our classical notion about the separateness of past and future breaks down. Part 12. Implications for the nature of time. The delayed choice experiment forces us to rethink something we have never really questioned, the nature of time itself. We experience time as flowing. The past is fixed and gone. The present is a knife-edge moment of experience. The future is open and undecided. This is the arrow of time, and it is so fundamental to our experience of being in the world that it feels like it must be a fundamental feature of reality itself. Physics has never fully been able to justify this intuition. The fundamental laws of physics, from Newton's mechanics to Einstein's relativity to quantum mechanics, are time-symmetric. Run any physical process forward, and the laws of physics will not complain. The equations do not know which direction time is supposed to flow. They work equally well in both directions. The arrow of time in the standard account comes not from the fundamental laws, but from the particular state of the universe at its beginning. The Big Bang produced a universe in an extraordinarily low entropy state, a state of very high order, and everything since has been an inexorable slide toward disorder, toward higher entropy. Because entropy only increases, and because the low entropy state is in the past, we can tell which direction time runs by asking in which direction entropy increases. This is a thermodynamic error. It emerges from statistics, from the behavior of enormous collections of particles. It does not tell us anything about the nature of time at the quantum level, where individual particles are subject to time-symmetric laws. The delayed choice experiment hints at something stranger still. It suggests that the quantum state of a system, its wave function, its set of potentialities, is in some sense suspended in time rather than moving through it. The correlations between the signal photon's behavior and the idler photon's future measurement exist in the quantum state from the beginning, from the moment the entangled pair was created. The sorting of past and future into separate, asymmetric categories seems to be something that happens at the level of classical measurement, not at the level of quantum reality. Some physicists, influenced by these kinds of experiments, have proposed radical reconceptions of time. One approach, associated with physicists like Yakir Haronov, is called the two-state formalism or time-symmetric quantum mechanics. In this approach, the quantum state of a system at any given moment is determined not just by what happened before the retarded state, but also by what will happen after the advanced state. The future, as well as the past, constrains the present. In this picture, the delayed choice experiment is not paradoxical. It is expected. Of course, the future measurement of the idler affects the present behavior of the signal, because the present quantum state of the system depends on both the past and the future. The state is, in a precise mathematical sense, a superposition of a state from the past and a state from the future, and both are real. This is not time travel. It is something subtler and more fundamental. It is the recognition that time, at the quantum level, may not be the one-way street we experience it as. It may be a fabric in which past and future are woven together, and the specific pattern of events, the history, emerges from the constraints imposed by both boundary conditions simultaneously. Part 13. The cosmic scale let us return to Wheeler's cosmic version of the experiment, because the scales involved add a dimension of drama that the tabletop version, for all its elegance, cannot fully match. The photons from a distant quasar that arrive at our telescopes tonight left their source when the universe was less than half its current age. They have been traveling through the void of intergalactic space for between 7 and 12 billion years. During that time, every major event in the history of our solar system occurred. The formation of the sun from a collapsing nebula, the accretion of the planets, the emergence of life on Earth, the rise and fall of every civilization that has ever existed. All of that history took place while these photons were in transit. And according to Wheeler's analysis, the question of what those photons were doing during their journey, whether they were taking a single path around the lensing galaxy or taking both paths simultaneously, does not have a definite answer until tonight. Tonight, when an astronomer in an observatory makes a choice about how to measure the arriving light, choice, according to the logic of the delayed choice experiment, retroactively determines what those photons were doing for the past 10 billion years. This has been discussed, seriously, in the physics literature. A team of physicists at MIT and elsewhere worked out the parameters of a cosmological version of the delayed choice experiment and argued that it is, in principle, if not yet in practice, performable using real quasars and real gravitational lenses. The quantum coherence would need to be maintained across cosmological distances, which is enormously challenging, but there is no known physical law that absolutely forbids it. If it were performed, and if it confirmed what the tabletop experiments suggest, we would have direct evidence that our measurement tonight determined the behavior of light that was traveling before the Earth existed. The idea that there could be a definite factual answer to the question, what was this photon doing 10 billion years ago? That was not available 10 billion years ago. But that becomes available only when we measure the photon today, is genuinely revolutionary. It is not consistent with any version of classical physics. It is not consistent with the everyday notion of a past that is finished and fixed. It is, on the other hand, perfectly consistent with quantum mechanics, which raises the uncomfortable question. If quantum mechanics is the correct description of physical reality, and all available evidence suggests that it is, then what does quantum mechanics say about the nature of the past? The answer, tentatively, seems to be, the past is not a complete, fully determined set of facts. The past is a set of quantum states, and quantum states are superpositions of possibilities. The specific, definite character of past events, the answer to questions like which path did that photon take, does not exist in the past itself. It comes into being when a measurement is made, whenever that measurement is made. The past, in this sense, is always being created in the present. Part 14. The Participatory Universe. John Wheeler spent the last decades of his life developing and refining the idea he called the participatory universe. It grew, in part, from experiments like the delayed choice experiment, but it reached towards something larger, a fundamental reconception of the relationship between observation and reality. Wheeler's vision was deeply informed by the history of physics. He had watched, in the 20th century, the progressive dissolution of the idea of an observer-independent universe. First, Einstein had space and time are not fixed backgrounds but dynamic entities that depend on the matter and energy within them. Then, quantum mechanics had shown that the properties of quantum systems are not definite before measurement. Now, the delayed choice experiment was showing that the act of measurement could reach backward in time. At what point, Wheeler asked, does the universe actually become real? His answer, increasingly radical as he aged, was that the universe becomes real through observation. Not in the idealist sense that there is no reality without a mind to perceive it, but in the physical sense that definite physical facts are brought into being by physical interactions that constitute measurements. The universe, he argued, is not a machine that runs on its own, producing definite outcomes at every moment. It is a participatory phenomenon in which the act of observation is constitutive of the facts observed. He used to draw what he called the Big Eye, a diagram of the universe as a U-shaped tube, with Big Bang at the bottom, the universe expanding through time up both sides, and at the top, an eye observing back down toward the origin. His point was that the observer, emerging late in the universe's history, plays a role in giving definite physical character to the universe's earliest moments. Every measurement made today on photons that have been traveling for billions of years is, in Wheeler's view, an act of creation. We are not merely passively recording a history that was already written. We are writing it. The act of observation, even today, even now, retroactively shapes the character of events in the deep past. This is not mysticism. It is not magical thinking. It is the straightforward extension of what the delayed choice experiment appears to demonstrate. Wheeler was simply following the logic to its conclusion and refusing to flinch from where it led. Part 15. The question of consciousness. This is perhaps the most dangerous section of the story, because it is where physics most easily bleeds into philosophy and pseudoscience and wishful. So let me be extremely careful. The delayed choice experiment does not require consciousness. It does not show that human awareness has any special role in determining the behavior of quantum systems. Observation that matters in quantum mechanics is not the act of a person noticing something. It is the physical act of an interaction between a quantum system and another physical system that creates an entanglement and thereby a record. A detector does not need a human observer watching its output to count as a measurement. A detector that sits in a sealed room and records photon impacts, with the data stored in a computer that no one ever looks at, is still performing measurements in the physically relevant sense. The photons in that experiment would still show particle behavior, not wave behavior, because the path information is still physically recorded, even if no human reads it. What matters is whether the which path information exists anywhere in the physical world, not whether any conscious being has access to it. This is an important point, because a great deal of popular writing, quantum mechanics, suggests that human consciousness plays a central role in collapsing the wave function and bringing reality into being. This is sometimes called the consciousness causes collapse interpretation, and while it has been seriously proposed by some physicists, including John von Neumann in the 1930s and Eugene Wigner later, it is not the mainstream, and there is no experimental evidence that distinguishes it from the more prosaic explanation in terms of physical entanglement. The universe was performing measurements long before consciousness existed, collapsed and exploded and formed new stars based on the outcomes of quantum processes, without any conscious observer present to collapse the wave functions involved. The quantum states of those ancient stellar systems resolved into definite outcomes through physical interactions with their environments, through a process physicists call decoherence, in which an entanglement with the environment effectively collapses the wave function without any observer required. What the delayed choice experiment shows is not that consciousness creates reality, but that reality is more participatory than we thought, in a purely physical sense. The act of measurement, even a purely physical act with no mind involved, brings definite facts into being. And if that measurement is performed on a particle whose quantum state has been preserved in superposition across vast stretches of time, measurement can, in principle, determine what the particle was doing during all that time. The history of the universe, at the quantum level, is not a fully written record sitting somewhere, waiting to be read. It is a structure of quantum correlations, and the definite, specific character of those correlations at any given point is brought into being by the measurements that interact with them. We are not the authors of reality, but we are, in a physically meaningful sense, one of its co-authors. Part 16. The limits of language. There is a reason this discussion has been so extended, so careful, so insistent on both the strangeness and the precision of what the experiment shows. It is because quantum mechanics is, in a very genuine sense, beyond language. All of our everyday words, particle, path, position, time past, future, cause, effect, were developed to describe a classical world. They refer to categories that make sense at the level of tables and chairs and planets and billiard balls. They refer to objects that are at definite places at definite times, traveling along definite trajectories, producing definite effects from definite causes. Systems are not like this. They are not poorly described by classical language. They are fundamentally incompatible with it. Every attempt to describe them using classical words involves either contradiction or metaphor or careful qualification. The photon behaves like a wave in some situations and behaves like a particle in others, but it is neither a wave nor a particle. It is a quantum system, and we do not have a word for what a quantum system is, because nothing in our everyday experience is a quantum system in the relevant sense. Wheeler knew this. He spent years trying to find the right language to describe the participatory universe, and he largely failed, as he acknowledged. Mathematics is precise. The experiments are clear. The conceptual framework, the story we tell ourselves about what is really going on, remains radically uncertain. This is not a failure of physics. It is a success. It is the discovery, hard-won and counterintuitive, that the universe is genuinely stranger than any story we are naturally equipped to tell about it. The strangeness is not a gap in our knowledge that will eventually be filled in. It is a feature of reality itself. The delayed choice quantum eraser is perhaps the clearest demonstration of this available to us. It is simple enough to explain in broad strokes, is precise enough to be experimentally tested and confirmed. It is strange enough to force a genuine confrontation with the limits of classical intuition. And what it shows, you strip up all the interpretative frameworks and the philosophical hedging and look at the raw data, is this. The universe does not maintain a complete, fully determined record of the past. The specific, definite character of past events is not fully established until present measurements bring it into being. The future measurement of the idler photon determines the past behavior of the signal photon in a sense that is physically meaningful, experimentally confirmed, and theoretically robust. Cause does not always come before effect. The past is not always finished. Part 17. What comes next? The delayed choice quantum eraser is not an endpoint. It is an opening. Demonstrates, with precision and repeatability, that our classical intuitions about the nature of time, causality, and the definiteness of the past are incomplete. But it does not tell us what the correct picture is, what the final story of quantum mechanics and time actually looks like. That story is still being written. In recent years, a new set of experiments has extended the logic of the delayed choice experiment in even more extreme directions. A 2019 experiment by physicists in Vienna, Inspire thought experiment proposed by Kaslav Bruckner, tested happens when the very choice of whether to perform a measurement or not is itself placed in a quantum superposition. In this quantum eraser with a quantum chooser, the experimenter's decision, the act of choosing to measure or not to measure, is entangled with other quantum systems. The result is that the photon appears to be simultaneously in a state of wave-like and particle-like behavior, a superposition not just of paths, but of the entire experimental context. This is getting very close to the idea that the distinction between quantum and classical, between the microscopic world of superpositions and the macroscopic world of definite facts, may itself be a matter of context rather than a sharp boundary. There is also ongoing work on quantum gravity, the attempt to reconcile quantum mechanics with Einstein's general theory of relativity. In quantum gravity, the structure of space-time itself may be subject to quantum superposition. Space and time may not be the fixed background against which quantum events occur. Space and time may themselves be quantum systems, subject to superposition, entanglement, and all the other strange features of the quantum world. If space-time is quantum, then all of our intuitions about the past, about fixed history, about the arrow of time, are built on a foundation that is not itself fixed. They are macroscopic approximations to a deeper reality in which the very geometry of the past is a quantum superposition. The delayed choice quantum eraser is, in this light, a window onto something truly fundamental. It is showing us the edge of the classical world, the boundary where our everyday understanding of time and causality begins to break down. Beyond that boundary lies the quantum structure of reality, where the past is not fixed, where the future can determine the past, where the universe exists as a superposition of all its possible histories, resolving into specific facts only through the participatory act of measurement. We are at the beginning of learning what it means to live in this kind of universe. Epilogue. The universe writes itself. There is a version of the story you have just heard that is comforting, and there is a version that is not. The comforting version says that all of this is just quantum mechanics, which only applies to tiny particles at microscopic scales. Your everyday life, the chairs and the cities and the people you love, these are made of so many particles governed by the statistics of such vast numbers of quantum events that the strangeness all averages out. The world you live in is effectively classical. The wave functions have all decohered. The histories have all been written. This version is, for practical purposes, largely correct. Quantum effects at the scale of everyday life. The delayed choice experiment does not mean you can change your past by thinking about it differently. It does not mean history is mutable in any way that affects human affairs. It does not mean the moon disappears when no one is looking at it, or at least not in any way that physics can detect. The uncomforting version says that the classical world you live in is an approximation, that at the base of every atom, every particle, every quantum of energy that makes up every see and touch and measure, there is this deeper quantum reality where time is not an arrow, where the past is not fixed, where the history of a thing is determined by what questions we ask of it. The uncomforting version says that the universe is not a story that was written before you arrived, that you are merely reading. It is a story that is being written now, in real time, by the interactions of every quantum system, with every other, by every measurement performed and every question asked. You are part of that process, not because your consciousness collapses wave functions, not because you are cosmically special, but because you are made of quantum systems, and everything you do, every measurement you make, every interaction you participate in, is part of the ongoing negotiation between past and future through which the universe becomes real. The delayed choice experiment proves that this negotiation does not respect the direction of time. The future reaches into the past. The present determines what the past was doing. The history of a particle, billions of years old, is not settled until today. In John Wheeler's words, no phenomenon is a real phenomenon until it is an observed phenomenon. The universe is not a completed recording playing out toward a predetermined ending. It is a living calculation, computing itself in real time, filling in the details of its own past as it goes, using the constraints of its future to decide what its history must have been. We are not spectators of this calculation. We are not even just participants. We are, in some small but physically genuine sense, instruments through which the universe observes itself, and in doing so creates itself. Cause and effect, past and future, observer and observed. The oldest rules in physics, the delayed choice quantum eraser, broke them all. And in breaking them, it showed us something true. The universe is stranger than we know. Stranger, perhaps, than we can know. But we keep asking, and the universe keeps answering,